Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Saya Dr. Agus Santoso Tamsir dari Departemen Teknik Elektro Fakultas Teknik Universitas Indonesia. Hari ini saya akan memberikan kuliah menggunakan video. Insya Allah akan saya upload ke YouTube saya yang memberi kuliah pada mata kuliah rangkaian elektronika yang akan saya berikan pada mahasiswa Departemen Teknik Elektro untuk semester genap tahun ajaran 2018-2019. Baik, kalau sudah lihat pertama-tama caption yang saya tampilkan adalah caption dari research group saya yang saya beri nama Micro Nano Electromechanical Systems atau disebut dengan MINA-EMS research group. MINA-EMS itu saya bergerak di bidang MEMS, Micro Electromechanical Systems. Dan kali ini, dan itu adalah bagian dari kelompok ilmiah elektronika di bawah Departemen Teknik Elektro Fakultas Teknik Universitas Indonesia. Baiklah, kita masuk ke tema. Ya, rangkaian elektronika yang akan saya ajarkan, saya menggunakan buku utama yang berjudul Electronic Devices and Circuit Theory yang dikumpulkan ya, diedit oleh dikarang oleh Robert L. Boylestad dan Louis Naselski. Yang saya punya di dalam PDF saya adalah tahun 2006, edisi tahun 2006. Ini yang saya gunakan. Kemudian yang kedua, ini sebagai pendamping saja, yaitu buku lama Integrated Electronics, Analog and Digital Circuits and Systems dari McGraw-Hill. Penerbitnya adalah McGraw-Hill International Book Corporation. Pengarangnya adalah Jacob Millmans and Christos C. Halkias. Buku ini terbitan tahun 1972. Nanti kita akan lihat tahun berapa terakhir buku-buku ini diterbitkan, dan saudara bisa membelinya kalau saudara mempunyai banyak uang di Amazon.com atau di Indonesia sebagian juga ada, saya tidak tahu di mana. Buku yang ketiga sebagai buku pendamping adalah buku karya Paul R. Gray, Paul J. Harst, and Stephen H. Lewis, and Robert G. Mayer. Buku ini berjudul Analysis and Designs of Analog Integrated Circuits, terbitan John Wiley and Sons, Inc., Singapura, pada tahun 2003. Kemudian buku yang keempat adalah buku karya dari Jacob Millman and Alvin Graber yang berjudul Microelectronics. Buku ini juga terbitan McGraw-Hill International Editions Electronic Engineering Series, Singapore, pada tahun 1948. Dan yang terakhir adalah buku karya Roger T. Wu dan Charles G. Sorini yang berjudul Microelectronics, An Integrated Approach, diterbitkan oleh Prentice Hall Electronics and VLSI Series, Prentice Hall Inc. Dari USA, New Jersey, USA, yang diterbitkan pada tahun 1997. Baik, kita kembali ke buku utama yang saya gunakan. Itu terdiri dari 15 chapter. Di mana saya hanya akan memberikan chapter 1, chapter 2, chapter 3, chapter 4, chapter 6, dan chapter 7. Kemudian itu diberikan pada setengah semester. Kemudian Bapak Taufik Alif Kurniawan akan memberikan pada chapter 5, 8, 9, 10, dan 11. Oke, kita mulai detail kuliahnya, di mana rangkaian elektronika atau dalam bahasa Inggris kita sebut dengan electronic circuits itu kita bisa jabarkan sebagai are composed by the collection of passive and active components connected to a certain position according to the applications. Jadi rangkaian elektronika itu terdiri dari komponen pasif dan komponen aktif yang terhubung, komposisinya tergantung dari aplikasi yang kita mau, yang kita inginkan. Sebelumnya kita lihat di sini contoh sederhana dari rangkaian. Ini rangkaian yang sederhana sebetulnya dari sebuah regulation circuit, fullback limiting series regulator circuit. Kalau kita lihat di sini, electronic circuits itu based on PCB, printed circuit board. Dia ada board, kemudian ada komponen pasif dan komponen aktif yang diletakkan di atasnya, dihubungkan satu sama lain tergantung keperluan kita. Kita bisa perkecil nanti sehingga ke dalam platformnya. Kalau yang pertama di platformnya adalah PCB atau printed circuit board, maka yang kedua platformnya itu adalah silicon wafer. Di dalam silicon wafer lah itu kita bangun rangkaian di mana komponen-komponen aktif ataupun pasif itu diperkecil, dibuat kecil, dan jalurnya sangat kecil sehingga memerlukan power yang kecil, tidak terlalu besar dibandingkan kalau kita gunakan PCB. Nah, pada bagian yang ketiga, circuit integrated circuit itu kita sebut dengan CMOS. Biasanya CMOS, analog dan digital. Dan pada bagian yang ketiga, kita membangun CMOS juga, integrated circuit, tetapi ditambahkan komponen-komponen yang kita bisa ubah dalam bentuk MEMS, yang dalam bentuk micro electromechanical systems. Jadi ada beberapa komponen, misalnya komponen filter. Itu kalau kita ganti dengan MEMS, maka bentuknya jauh lebih sederhana. Dan ini digunakan pada sirkuit masa sekarang, contohnya pada smartphone. Itu menjadi hanya kecil, tipis, tapi bisa punya kemampuan feature yang sangat baik disebabkan oleh sistem yang digabungkan antara CMOS dengan MEMS itu sendiri. Kalau saudara lihat di sini electronic circuitnya yang base berplatformnya PCB, printed circuit board. Ini saudara bisa lihat gambarnya seperti ini. Ya, nampak di situ PCB yang dimana di atasnya ada pasif komponen ataupun aktif komponen, ataupun digabung dengan integrated circuit dan dibuatkan jalurnya yang menghubungkan satu sama lain sesuai dengan keperluan kita. Kemudian kita pindah ke integrated circuit di mana itu berada di dalam satu chip IC yang di dalamnya terdapat bermacam-macam pasif ataupun aktif komponen. Dan di sini yang saya tampilkan adalah sudah dia menggunakan IC CMOS ditambah lagi dengan fotonik. Kenapa? Ini untuk memenuhi kebutuhan dari padatnya kapasitas yang diperlukan pada satu sistem saat ini. Saudara bisa bandingkan nanti pada bagian akhir akan saya tampilkan video tentang photonic integrated circuits. Kemudian saudara bisa lihat di caption berikutnya adalah gambar desain dari integrated circuits yang sudah lumayan rumit, tapi untuk saat ini ya biasa saja sebetulnya, karena banyak yang jauh lebih rumit lagi, untuk jadi dari jutaan transistor. Dan kalau saudara lihat MEMS di sini, ini adalah desain MEMS yang digunakan untuk untuk apa namanya, proyektor yang kita pakai sekarang, dimana bagian yang bergeraknya yang mengubah besar terang gelap dan warna itu menggunakan konsep MEMS. Kemudian berikutnya kita bisa lihat sebuah rangkaian CMOS MEMS oscillator monolitik. Artinya bagian MEMS dengan bagian CMOS itu bersatu dalam satu buffer yang berfungsi untuk menghasilkan mengosilasi RF ya biasanya, dengan hasil yang jauh lebih memuaskan daripada kalau kita menggunakan purely CMOS. Selanjutnya kita bisa lihat sebuah monolitik CMOS MEMS IC dari sebuah gyroscope. Gyroscope ini banyak kita gunakan di dalam smartphone. Baik, dari pernyataan bahwa dalam rangkaian elektronika sebelum tadi, kita bisa nyatakan bahwa ada dua kata penting yang perlu kita perhatikan dalam hal komponen, yaitu pasif komponen dan aktif komponen. Menarik untuk disimak, karena nanti kita akan di dalam rangkaian elektronika, kita hanya akan fokus pada aktif komponen. Baik, pasif komponen itu yang kita sudah kenal sebelum ini, ada 3, yaitu resistor, kapasitor, dan induktor. Sementara aktif komponen adalah diode, bipolar junction transistor atau BJT, dan field effect transistor. Gambar pada caption ini menggambarkan beberapa macam komponen electronics, pasif terutamanya, maupun aktif, dan yang berukuran kecil, yaitu surface mount parts. Ada BJT, ada BJT, ada CMOS, ada BJT, ada GFET, ada FET, ada kapasitor, ada diode, dan ada resistor. Kita lihat pada pasif komponen, di sini diode, di sini resistor. Saudara bisa lihat beberapa jenis resistor bergantung dari berapa watt mampu resistor tersebut digunakan, dan ada bar pita-pita warna yang menunjukkan berapa ohm ukuran dari resistor itu. Kalau kita bedah di dalam dari resistor, maka kita akan lihat ada karbon composite yang diselimuti oleh insulator. Kemudian di bagian ujung-ujungnya ada kawat yang menghubungkan bagian dari karbon composite dengan dunia luar untuk membentuk rangkaian. Dan kalau kita lihat rumus daripada resistansi, itu sama dengan Rho L per A, di mana Rho sama dengan resistivitas dengan satuan ohm meter, kemudian L dalam satuan meter length, dan A adalah merupakan cross section area atau penampang melintang dalam satuan square meter. Nah, bahan yang kita tempatkan di dalam sebuah resistansi itu diukur dari dapat kita wakili dengan nilai resistivitas. Dan silver itu mempunyai resistivitas 1,645 dikali 10 pangkat 8 pada suhu 20 derajat Celcius, dan seterusnya sampai yang paling besar adalah 1,1 dikali 10 pangkat 16 ohm meter, yaitu Teflon. Kalau sudah kita mau membuat resistor dengan besaran tertentu, maka kita bisa memilih bahan apa yang akan kita gunakan. Tentunya yang memiliki resistansi lebih besar lebih baik. Dengan hanya sedikit bahan kita bisa mendapatkan resistansi yang sesuai dengan keinginan kita. Kapasitor, saudara bisa lihat di sini bermacam-macam jenis kapasitor. Ada tantalum, ada ada bermacam-macam jenis kapasitor. Yang kita bisa lihat di sini tantalum. Kalau kita belah, maka di dalamnya ada bahan tertentu yang mempunyai nilai mempunyai nilai dielektrikum tertentu. Kemudian di tengah-tengahnya, di pinggir-pinggirnya ada dua elektroda. Konsep dari kapasitansi adalah ada dua elektroda, di mana di tengah-tengahnya ada medium, ada bahan yang kita letakkan di situ untuk membentuk nilai kapasitansi. Kalau kita lihat di sini, nilai kapasitansi tergantung dari persamaan 10/3. Nilai kapasitansi kita bisa ukur dari epsilon R A per D dengan satuan farad, di mana epsilon R adalah relatif dielectric constant, dan besarnya untuk vakum itu 1, udara 1,0006, keramik dari 30 sampai 7200, dan seterusnya. Dari situ kita bisa dapatkan nilai kapasitansi yang mana yang kita inginkan. Kita bisa lihat dari contoh ini, ada dua elektroda yang di tengah-tengahnya udara. Dengan satuan tertentu kita dapatkan besaran kapasitansinya adalah 200 picofarad. Kemudian kalau kita isi keramik di dalamnya dengan high permittivity, misalnya 7500, maka kita akan dapatkan kapasitansinya sebesar 1,5 mikrofarad misalnya. Dari situ kita bisa lihat bahwa besarnya dielektrik yang kita sisipkan di antara dua elektroda akan mempengaruhi nilai kapasitansi yang kita ukur. Kapasitansi juga bisa dibentuk dari paralel kapasitans, misalnya yang disebut dengan stack kapasitor, dengan berlapis-lapis kemudian digulung. Dari situ kita hubungkan di bagian elektroda plus elektroda minusnya. Ataupun ada tubular kapasitor. Oke, kita tidak akan terlalu jauh bicara di sini karena bukan di sini yang kita fokuskan. Kemudian induktor pada pasif komponensi yang lainnya adalah induktor, di mana ada kawat yang dililitkan, sehingga kalau diberikan arus maka dia akan menghasilkan medan magnet. Dan kalau medan magnetnya di tengah-tengah bagian kumparannya itu kita ganti dengan besi yang berbeda-beda, maka nilai induktansinya juga akan berbeda-beda. Rumusnya adalah L sama dengan mu n kuadrat A per L, di mana mu adalah besaran dari bahan yang kita gunakan untuk membentuk besaran kapasitansi, kemudian induk berapa lilitan kita lakukan, dan ukuran lilitannya kita bisa lihat dari A ya. Kemudian panjang yang kita lilitkan kita bisa lihat dari L. Nah, itu kalau kita hitung maka akan kita dapatkan besaran induktor yang kita peroleh. Baik, ini adalah fokus kita sebetulnya. Fokus kita adalah pada active components. Pertama, diode sebagai bagian aktif komponen yang kita perlu perhatikan. Yang kedua adalah bipolar junction transistor. Dan yang ketiga adalah field effect transistor. Baik, kita lihat kemudian dari pendekatan yang lain. Pada aktif komponen kita fokus melakukan kajian menggunakan semikonduktor, dan terutama kita gunakan pada golongan 4. Karena kita akan mengarah ke nantinya pada advance electronic circuit, kita akan mengarah pada integrated circuit terutamanya. Dan integrated circuit biasanya menggunakan silikon karena bahannya banyak di dunia, sehingga bisa menekan harga jual. Nah, semikonduktor itu, katakanlah silikon. Semikonduktor itu, katakanlah silikon. Itu bisa kita kaitkan dengan metal, dan akan menghasilkan untuk elektroda untuk metal tertentu yang dilekatkan dengan semikonduktor tertentu, itu bisa saja tidak bisa dilewati arus di situ. Untuk kondisi tertentu bisa saja tidak bisa dilewati arus. Tapi ini tidak menarik buat kita. Kita akan langsung masuk ke PN junction. Jadi yang kita akan lakukan adalah merekayasa semikonduktor. Kalau kita tahu misalnya silikon itu mempunyai valensi 4, artinya pada kulit terluarnya memiliki 4 elektron yang akan langsung mengikat pada atom di sebelahnya apabila terjadi berdekatan. Nah, keempat elektron yang ada inilah yang kita rekayasa sehingga bisa menghasilkan semikonduktor yang tipe P kalau dia kekurangan 1 elektron, atau tipe semikonduktor yang tipe N yang kalau dia kelebihan elektron. Nah, ini yang hasil rekayasa inilah yang kalau dua semikonduktor ini, tipe P dan tipe N itu kita dempetkan, maka kita mendapatkan satu peralatan, satu device yang kita sebut dengan diode. Dalam kajian ilmiahnya kita sebut, sebelum kita nyatakan sebagai diode, maka kita sebut sebagai PN junction. Nah, kalau kita rekayasa dia PNP, kita dekatkan dengan satu proses tertentu, atau NPN, maka kita akan diperoleh transistor bipolar junction transistor. Sedangkan kalau kita bentuk tertentu seperti pada gambar ini, kita bisa menghasilkan MOSFET atau field effect transistor. Nah, ini yang perlu diperhatikan. Kemudian kita kembali ke table of content ya, daftar isi dari buku yang kita gunakan. Tadi sudah saya katakan ada 15 chapter yang ada di dalam buku itu. Dan kita hanya membahas sampai 11 chapter karena keterbatasan SKS kita. Nah, dari 11 chapter itu kita lihat komposisi utama dari isi chapter itu adalah Chapter 1 dan chapter 2 kita bahas semikonduktor dalam kaitannya dengan diode dan aplikasinya. Kemudian chapter 3 kita bahas bipolar junction transistor. Di chapter 4 kita bahas bagaimana bipolar junction transistor dicatu DC, efek yang akan terjadi. Dan kita perlu tahu kenapa kita catu DC, karena transistor itu bersifat memperkuat, ya. Dia adalah penguat. Tidak akan mungkin terjadi penguatan kalau tidak ada energi lebih, energi yang kita catu ke dalam transistor itu. Oleh karena itu kita mesti catu DC supaya kita bisa dapat penguatan di dalam sistem outputnya. Maka kita perlu mempelajari DC biasing. Juga di chapter 6 dan 7, chapter 6 kita belajar tentang field effect transistor. Ada junction FET, dan satu lagi ada MOSFET, dan seterusnya. Dan seterusnya adalah AC, ya, analisis AC. Kemudian chapter 8 juga kalau kita gunakan FET untuk amplifier, dan chapter 9 kalau kita lihat frekuensi responsnya, kita sudah memasukkan AC di situ, AC analysis. Kemudian chapter 10 kita sudah mulai membicarakan sebuah operational amplifier. Kita tahu nanti ini cerita ke depan saja, kita tidak usah bahas sekarang. Baik, berkait dengan active components, salah satu hal yang mengawali begitu banyaknya perkembangan seperti saat ini adalah mulai berkembangnya penggunaan device memanfaatkan semiconductor. Kita lihat pada tahun 1947 ada 3 orang peneliti di Bell Laboratory, masing-masing adalah Dr. Shockley, Dr. Bardeen, dan Dr. Bradtain, mulai mengembangkan sebuah transistor BJT seperti sudah lihat pada gambar ini, yang berbahan dasar semiconductor. Pada saat itu mereka mencoba menggunakan bahan semikonduktor germanium golongan 4. Mulai dari saat itu berkembanglah bermacam-macam inovasi-inovasi, inventor yang akhirnya kita ketahui seperti sekarang ini. Kita bisa lihat di sini. Tapi sebelum berkembangnya semiconductor PN junction, memang sempat dulu berkembang metal semiconductor contact pada tahun 1874, kemudian light emitting diode pada saat tahun 1907. Tapi masih pendekatannya sangat primitif kalau kita lihat dari sekarang. Kemudian pada tahun 1947, yang seperti saya katakan tadi, berkembang bipolar transistor. Pada tahun 1952 mulai berkembang thyristor, kemudian 1954 solar cell, 1957 heterojunction bipolar transistor, 1958 tunnel diode, 1960 MOSFET, laser pada tahun 1962, heterostructure laser pada tahun 1963, kemudian transferred electron diode pada tahun 1963 juga, impact diode pada tahun 1965, MESFET 1966, non-volatile semiconductor memory pada 1967, charge coupled device pada tahun 1970, resonant tunneling diode pada tahun 1974, MOSFET pada tahun 1980, room temperature single electron memory cell pada tahun 1994, dan tahun 2000 ditemukanlah MOSFET dengan jarak antara source dan drain sebesar 20 nanometer.
All right, so thanks to Susan for the lovely introduction, and thanks to OSA for inviting me here to speak. So I'm going to talk a little bit about the research that we're doing in silicon photonics at IBM and give a little bit of an industrial perspective. So all of you may not have direct experience with data centers, but I can guarantee you that all of you have probably accessed a data center multiple times already today. Here's a picture of a Google data center, and they're basically large warehouses full of computers, and they're used by any company, any institution that is storing and analyzing a whole bunch of data. So it's just a warehouse full of computers, and all these computers need to talk to each other. So we have a little bit of an issue. These data centers can be, the size of football fields. So if you're trying to transmit data over a short distance, say, you can use a copper cable. But as our data transmission speeds get faster and faster, the length that you can go over copper gets smaller and smaller. So now we're at less than a meter. And of course, the other answer there is fiber optics. And we're very familiar with that. Fiber optics is the backbone of the internet over these very long distances. So that's great, but currently a lot of the technology that's used for the internet, there aren't so many links. If you want to send information from here to California, you're talking maybe tens of thousands of parts per year. You can afford to have very complex machinery, very expensive machinery. It's a low volume, high margin industry that has extremely high performance. So what we want to do is find a technology, hopefully an optical technology, that will bridge the gap, that will cover these distances in a data center from, say, hundreds of meters to several kilometers, and that will do that with a lower cost so that it becomes really a viable technology for these high volume applications, but that still keeps the performance that we need. Another application that is asking for a technology like this is high performance computing or supercomputers. Again, not something that everybody uses every day, but I'm sure that you've looked at the weather predictions. Some of you, may have at least read about or have experience with some of these research applications. Any large-scale simulation is done usually on a supercomputer like this. Finance analysis, smart grid, there are a lot of these applications that are run on supercomputers. And here's an example. This is the Sequoia IBM Blue Gene Q system. This was, when it came out, it was the #1 supercomputer. Right now, it's sitting at #3 on the top 500 list. And all of these orange cables that you can see here, these are all optics. So there's about 1 million optical fibers that are supporting this very large supercomputer. But the technology right now is still, these are manually assembled parts. They have, components that you've got little lenses, little lasers, little detectors that are all put together, usually in large factories. So it's still a fairly expensive technology. Right now, the cost of these optical interconnects is around 10% of the total system cost. And that's all right for now. But if you project going forward, we can look at the estimations, and very rapidly, the cost of the optical interconnects go above 100% of the total allowed system cost. And you can't really have that. I mean, you need to have some funds left over to buy the actual processors. So this is another application where we're really looking for a low cost, but still high performance technology. And so, of course, when the community saw these problems, one place that we looked, and probably the first place that we looked, is to silicon, because we know a very high performance, large volume technology, and that's the complementary metal oxide semiconductor CMOS process that provides all of our computer chips today. So they're produced on these large silicon wafers that can provide many chips, so high volume keeps costs low. And it's also extremely advanced technology because it's been developed for so many years in such an important industry. So they get ultra high yield that's required. If you have to produce 1 million parts per year or several million, you can't have half of them failing. They really all have to work. So we would get ultra high yield and also the dimensional control that we need to provide high performance optics, at least that we would like. But of course, this is an electronics process. So the question is, can we add optics? And of course, the first problem is that silicon is unfortunately not a very good optical material. So that was the first hurdle to jump over. But over the years, the community has put a lot of research effort and a lot of time. And in fact, we've made it a pretty good optical material. We can get pretty much matching performance from silicon in many of the components that we need for optical data communication. So this is great. We can do it on silicon in the lab. But the other issue here is that in order to get these ultra high yields and dimensional control, there are very tight process controls in CMOS fabrication facilities. So if I went to somebody who works in a CMOS fab and I asked them, okay, well, can we just change this etch time by 5%? Can you do that? They'll have a conniption fit. You can't do that and still keep the performance and the reliability that you need for this type of very fine scale technology. So it's been quite a development effort to bring these two things together. But we at IBM have been doing that over the past 10 or so years, and also, of course, other institutions have been working on the same project. But what we've done at IBM is we took a standard CMOS processing flow, a number of steps. This is what everybody is comfortable with in the CMOS foundry. And we just added a couple of things. So we added a couple of levels here and there to make our optical devices. So what we've done is we had a minimal changes that everybody signed off on. You know, you have to get, to make these changes, you have to get sign-offs all up and down the chain, people running around in circles. But we convinced them that this was okay. And so now we have photonics as a new feature in standard CMOS. So what we can do is we have our regular transistors here, like you would have in any computer chip, right next to it. In fact, on the same level of silicon, we could have these optical devices, a modulator that turns the light on and off. Oh, what just happened? That turns the light on and off to take the electrical signal and put it into an optical signal. So we get light pulses out. And then we have a detector that reads in that optical signal, all those pulses, transfers those pulses back into the electrical domain. So what we have here in this single chip is a monolithically integrated silicon photonics technology. So IBM had the first sub-100 nanometer node monolithic technology. This is important because the smaller the node, the better the performance. So our technology is good for 25 gigabit per second operation, which is where the market is right now. That's what everybody's asking for. And we can make these in very large scales. We can supply the market of millions and millions of parts. And we can do that by taking advantage of all of the CMOS infrastructure that's there already for electrical chips. So everything is basically the same, except for a couple of changes that we've made. And one additional point I want to emphasize here is not only are we taking advantage of the highly advanced CMOS fabrication technology, all the equipment, the silicon, the machines, the metals, we're also taking advantage of all the software and enablement tools, the whole package that come along with that. So if you're, currently the state of most of the optics market right now is you'll be a graduate student, or you'll be a PhD working in a company, and you'll take one, or maybe if you're doing a heroic experiment, you'll connect a couple devices together, and you'll design all of those, you'll put them all together, you have to understand all of the physics behind it, and then you can do your experiment. You'll have a couple of components. So in that case, you can do all of it yourself. You can understand the devices, how they work. You can put it together. It takes maybe how much training? 15 years of training altogether to be able to do that, but you can do it. But in the electronics industry, there are millions and millions of transistors in every single computer chip. If we want to take that as a model, if we really want to get there with optics and have this large complexity, large scale integration, we want to make this simpler so that not everybody has to be a device designer. You can't both design the transistor and design the architecture of your computer. It's too much for one person. So what this infrastructure in CMOS enables us to do is, for example, we'll have a library of components. In this case, we provide both electronic components and photonic components. That's already provided to you as the designer. So you can just place them together, those are all qualified. They have, they're guaranteed to produce the same way every time within a certain range of parameters. They have models associated with them. You can do simulations so that you know how the system is going to work. We've got design rules such that if your waveguide has a gap in it, it'll flag and let you know. And we have matching of layout and schematics so that you know that what you made is actually what you wanted to make. And that's what's, I would call this a real qualitative change in the way that optics designers are doing their designs. Because it's, rather than just doing a couple devices together, it's really necessary. This isn't even a particularly large system I'm showing it, this is just an example, but in order to build something this large, you really need to have all this verification. You can't do it all by hand, it's too much. So using the CMOS technology lets us lay out complex both electronic and photonic circuits without having a PhD in optical device physics, which enables, I think, the design of new levels of hierarchy of complexity. And there are a number of potential impacts going forward. I think silicon photonics is a pretty well-hyped field these days. It's very exciting. Nearer term are the applications that I've talked about in data centers, cloud computing, web search, also high-performance computing, large-scale simulation, drug discovery, data analytics. Big data is a big thing these days. Also some applications in networks, maybe moving into the telecom space somewhat, depending on, performance requirements and cost. Over the longer term, of course, this is very speculative. There's a lot of research that needs to be done before we can get there, a lot of performance improvements. But I think the community has a really good start on these things, and so we can look forward and hope that eventually this technology will make its way into personal computing for maybe data transfer when we need, I don't know, a video screen this big with millions and millions of pixels. Maybe you would need this kind of technology. Many core systems, you can imagine having all of these CPUs together. If they're producing even more data than they are now, the electrical connections aren't going to work even over these distances. So we can imagine a chip that's interconnected with optics between the memory and the CPU, between all the different cores. These are forward-looking applications, but these are what we're hoping for. And then there are also other applications. People are using silicon photonics as disposable lab tests. Say it's a cheap silicon chip, you can do it, you can do your optical testing, you can throw it away. And environmental sensors, and also I think there'll be some new applications that we're not even aware of right now as we move from the several transistor model to the millions and millions of transistor model in photonics. Once we have all these components, there are new things that we're going to be able to do. And I just want to briefly also give a background of my path, since this is sort of about women in optics and our experiences. So I'll say in childhood, I had a somewhat unusual experience in that none of my immediate family, my parents, none of them were scientists. So I sort of got into that, I don't know how exactly, on my own. And I had a great interest in these popular science books. So that was really my gateway. And I was always encouraged by everyone who saw me reading these books to really go on in science. So I was lucky in that sense. And then I did get an early start. When I was 13 years old, I attended the Mary Baldwin College. It's a program for exceptionally gifted. It's a program for young students to start college early. And after a year there, I transferred to Bryn Mawr College, where I got my bachelor's in physics. And I will say both of these schools were women's colleges. And for me, that did have a large impact. Especially, I mean, I knew myself as a young student. I felt more comfortable in this sort of nurturing environment. It was small, got a lot of interaction time with the professors, a lot of female role models. It was great for me. I do also want to say, these sort of small classes, nurturing environments are often presented as a women's issue, that women will be more likely to stay in physics and optics if we have these nurturing small environments. I'd rather say this is a people issue. Women span the whole spectrum. Some are very, go-getter and aggressive, and they would love to be in a more competitive environment. Some of us, I wanted for the beginning of my career to have a lot of confidence and to be in a nurturing environment so that then I could go forth. But I think there are a lot of men also who would benefit from that experience. There's many different ways to do things. So after this experience, At Bryn Mawr College, I went to California Institute of Technology for my PhD, and I will say that was definitely a hard-charging, competitive environment, and I really benefited from the confidence that I developed in my undergraduate career, where I had a lot of support and a lot of mentors. And then after that, I moved into industry, mostly because I wanted to make something. It was exciting to me, the idea of going out there, working for a company that has access to the resources to take something that we design and put it out in the world. So that's what I've been doing. I also want to highlight OSA's role really throughout my career, going to conferences and now more participating in conference committees, peer review, and now being an associate editor for a journal has really connected me with all these other researchers in the field. It really, one, it gives you a bird's eye view of what's actually going on, what's important. It lets you see, oh, maybe that'll be the next big thing. There are a lot of papers on that. It also builds professional collaborations, or even just knowing people. If you have some question in your lab, you say, oh, I think I know that guy who's an expert in it. I'm going to send an email. And usually they'll answer. So OSA has been very helpful in that for me throughout my career. And just want to thank the team. Through all IBM folks working on this project. And thank you.
Hi, I'm Max Millett. I'm a postdoc here at UC San Diego, working with Professor George Porter. My research focuses on designing energy-efficient and high-speed communication networks for data centers. Data centers are the physical infrastructure that companies like Google, Facebook, Microsoft, and Amazon use to provide online services to billions of people across the world. A data center is a warehouse-sized building housing tens of thousands of computers, and those computers are connected together using a network that allows them to work together to process large amounts of information. And as data centers grow to support more users and services, it's becoming increasingly difficult to design high-performance, energy-efficient networks. Today, data centers consume about 2% of all the electricity used in the United States, and that number is projected to double in the next decade. Here at UC San Diego, we're working on technologies to improve the performance and energy efficiency of data centers. Our focus is on eliminating bottlenecks in the network so information can flow between computers at a faster rate, allowing them to finish their computations quicker and use less energy. One of the main bottlenecks in today's networks are the electronic switches that are used to route information from source to destination. And we can use optical switches to replace these electronic switches. Optical switches carry information as light and allow information to be delivered to the destination at much higher rates. Making optical switching practical in data centers requires innovation at a number of different layers. And to address this, our research spans everything from the hardware to the software that controls how information flows across the network. At the hardware layer, we're building prototype optical switches designed to meet the specific requirements of data centers. And we're also working on the control and communication protocols required to make today's networking hardware work with optical switches. One of the great things about working in the CSE department here at UC San Diego has been the collaborative culture, which has really been a big enabler for this type of interdisciplinary research we're doing. And looking forward, we're working on reducing the barriers to adoption for optical switching, with the ultimate goal being to impact the design of next-generation data centers.